On with secondary compression, I wanted to talk about a scale effect and what we call hypotheses A and B with respect to how that scale effect might impact secondary compression. Let's first talk about the scale effect. Okay, when we test a soil specimen in the laboratory, its thickness is usually pretty small, generally about 20 millimeters. I mean, lab specimens may have some variability in their thickness, but usually about 20 millimeters, which is about an inch, something like that. So when we apply a load to the top cap shown here, by the way, this is the top cap and then a top porous stone and the bottom porous stone. So we have double drain conditions. Water can flow up or down through the soil. When we apply the load, the water usually squeezes out pretty quickly and consolidation will move along fairly fast. I mean, it's often typical to leave a consolidation stage on for 24 hours, and that's usually enough time to clearly see a secondary compression slope. For most kinds of soils, if the permeability is really low, maybe it will take longer. But anyway, consolidation is generally done in a matter of minutes or hours for a specimen that's only 20 millimeters thick. Okay, then we go to the field, and real soil layers vary by a lot. You could have really thick clay layers, like marine clay layers in the Gulf of Mexico, or something like that could be tens of meters thick, maybe even more than that, very thick clay layers. Maybe you could have a few meters in some fluvial environments, but anyway, we're dealing with something that's much, much thicker than the 20 millimeter thick laboratory specimen. Now what we're doing is assuming that the laboratory soil behavior is representative of what happens in the field. And I think for compressibility, that's a pretty reasonable assumption, right? Because we're adding some load and we can measure how much it settles for primary consolidation. For secondary compression, it's a little bit more complicated because this layer in the field is going to take maybe years to consolidate, right? Whereas this one in the lab only takes a day. This one in the field might take 30 years. So how much secondary compression happens during primary consolidation for the lab specimen might be different than the amount of primary consolidation that happens for this field layer that's going to take many years to consolidate. And again, I'm using the definition of secondary compression here that is dE dt at constant sigma v prime. So I'm not using the traditional definition of secondary compression. I'm assuming that some secondary compression can happen. So what I really mean is like how much dE dt at constant sigma v prime is going to happen during primary consolidation for these two different layer thicknesses and times to consolidation. All right, so I've already said this, the drainage path is much shorter for the lab specimen than for the field layer, therefore it consolidates much faster. The important question we're trying to answer here is, does more secondary compression happen for the field layer than for the laboratory specimen? And if it does, that means that maybe what we're measuring in the lab is not going to be representative of what actually happens in the field. We might have to make some sort of adjustments for the time scales and the amount of secondary compression that might happen in the field that's additional to what would happen in the lab. So there are two hypotheses here that kind of bound the range of possible behaviors. So hypothesis A, here is hypothesis A, that's that the amount of dE dt at constant sigma v prime that occurs during primary consolidation is the exact same for a lab specimen and for a field layer. So even though the field layer may take 30 years to consolidate, whereas the lab specimen might take 30 minutes, the dE dt at constant sigma v prime for those two soils will be the same. Okay, and what that means, and I'll show you this in just a second, that means that the normal consolidation line, right, the line that has a slope of cc, where you're moving along that normal consolidation slope, at the end of primary consolidation is unique. So you measure the curve from a thin laboratory specimen, it's going to be the same as if you measure it for a very thick laboratory specimen. The added time that it takes to consolidate is not shifting that line around due to secondary compression. All right, now this will become clearer in just a second, and I'll repeat some of these concepts. We move on to hypothesis B, and that is that the amount of dE dt at constant sigma v prime that occurs during primary consolidation is more for the field layer than for the laboratory specimen, because it takes a lot longer for the field layer to consolidate, right? So if there's some amount of secondary compression that's always happening, it makes sense that there would be more secondary compression happening in the field than in the laboratory. And that means that by the time we reach the end of primary consolidation, the soil would actually be at a lower void ratio in the field than in the laboratory, because that secondary compression has contributed to reducing the void ratio during primary consolidation. All right, so this set of figures right here sort of explains hypothesis A and B and the difference between them. And in this class, we're going to use them both. Right? We'll run computer programs that run hypothesis A, and we'll run computer programs that use a variety of hypothesis B. These hypotheses aren't necessarily prescribing a certain procedure for how secondary compression is computed. It's more just an overarching idea. So anyway, let's talk about the idea. That's the goal right now. So the thin specimen is here. This is log time. It consolidates quickly and goes into secondary compression, right? So this would really be a lot of secondary compression. We've let this laboratory specimen go on for 30 years. We get a lot of post-primary slope there. Then hypothesis A is that if we did the field test, right, tested a much thicker layer in the field, the curve would basically have the same shape as the thin specimen. It would just be shifted to the right. So it's going to take a lot longer for it to consolidate. So you get this blue line here, and then it'll have a vertical offset, right? Because the amount of primary consolidation goes along this horizontal line that's following the mouse. Maybe I'll even sketch in green, like a dashed line right there. Right? So the black and blue lines are both ending primary consolidation at the same strain or at the same void ratio. And then secondary compression starts, right? So that's hypothesis A. Hypothesis B is that there's going to be secondary compression happening during primary consolidation, and the void ratio is going to be reduced as a result of that. So we're following this red line now instead of the blue line. And when we get out to a really long amount of time, the red line is going to merge with this thin specimen line and become the same. Now that's how hypothesis B is usually explained. It's not necessarily the case that they'll merge together, but it is the case that the line for hypothesis B will be lower. Now this is an important distinction because if we have a really thick clay layer, right, we may significantly underpredict settlement if we assume hypothesis A is right, but actually hypothesis B is right. So it's important to understand these differences and think through the implications of that. All right, then this figure over here shows the different hypotheses, hypothesis A and B, but instead of being void ratio versus log time, we now have void ratio versus log vertical effective stress. So here's the normal consolidation line that you would measure at the end of primary consolidation. So let's say that you got your 20 millimeter thick specimen, you did a consolidation test, you loaded it up to vertical pressures that were higher than the maximum pass pressure in the field, you can get this normal consolidation line, right? And measure the slope C sub C. Let's say that we had a load stage that started here at this vertical effective stress, right? And ended here at this vertical effective stress. And that we're going to go and touch the normal consolidation line, right? So it's starting out a little bit over consolidated, and then it hits the normal consolidation line and becomes normally consolidated, goes on the C sub C slope. Then we're waiting for some time so that we're going to get secondary compression and it's moving down. All right, now according to hypothesis A, the field test shown in blue here on a very thick specimen will follow the exact same stress path as the laboratory specimen. So when we reach the end of primary consolidation, the void ratios will be exactly the same, and then we will start secondary compression, right? And these two stress paths will give you the exact same result. So hypothesis A is pretty useful because it means we can directly take the laboratory results and estimate what's going to happen in the field for a much thicker layer with only doing some very basic manipulations that I'll talk about in another lecture. On the other hand, if hypothesis B is right, then we're not going to follow the same stress path. There's going to be more secondary compression happening during primary consolidation, so we'll be below the stress path for the laboratory specimen, and we'll end up having a curve that's something like that down here for hypothesis B. Okay, and I wanted to just end this lecture by talking about the timeline concept that was originally formulated by Bjerrum in 1967, I believe in the paper for his Rankine lecture. So the timeline concept is basically used to describe hypothesis B, or to explain this idea that the normal consolidation line is not actually unique, right? It depends on the amount of time it took you to get there. So if you measure the normal consolidation line for a 20 millimeter thick specimen, right, you're measuring a line at T equals TP. So the amount of time that elapsed was TP for that laboratory specimen. Maybe it's 30 minutes or something like that. Okay, if you were to adjust the thickness of that specimen so that it took 10 times longer to reach the end of primary consolidation, you would have gotten some secondary compression happening now during primary consolidation, which means that, according to this concept showing the red lines up here, your load stage would end up at a lower void ratio. That means that you're going to measure a normal consolidation line that's a little bit lower. Sorry, I'm trying to scroll here. There, we got it. So 10 times TP, you have a line that's lower. 100 times TP, it's lower yet. 1,000 times TP, and it's lower still. And the distance between these is equal to C alpha, because the amount of time is an order of magnitude in each case. So this timeline concept can be really a useful mental model for kind of understanding how hypothesis B might result in more settlement than hypothesis A. And we'll see this later when we start running different computer codes that implement these methods.